Hi, welcome to our last lesson in 1.4, matrix multiplication, A times B and C times R. In the last video, in the last lesson, what we were looking at and focusing on was when I take a matrix and I break it into the CR multiplication, we started with finding C. So it was all about looking for those linearly independent columns, and then from that, trying to discover what the combinations were that would construct the dependent columns, and that created my matrix R. And one of the big driving questions in that lesson and in those problems was when I'm looking for those linear combinations, some stood out to us and some didn't. Like, we need a procedure. And I'll be honest, like, a lot of having taken this kind of course a couple different times, I'm itching to get into this procedure because I'm a very procedure-minded person. I love teaching concepts because I think that's the best way to get a grip on why we do what we do. But when we're talking about all of these concepts, you just want to get into the actual calculations. And what's nice is that this lesson, once we begin to talk about these, will lead us into the next chapter and really start hitting on a lot of these. So I'm going to highlight a couple things that we're doing and really emphasize a couple things that may get expanded on more in chapter 2. So even if in here what we talk about doesn't make a ton of sense as to why we have the equality, like why the train of thought is good, hopefully I can justify it enough where you can almost blindly accept it from now, because then again we'll prove it and we'll add more terminology and things as we go. It's kind of a welcome to Unit 1 in terms of a math course. And so and really to get us started, we have this matrix A. It has 3 different columns. So we have an M dimension of 3, so 3-dimensional. And even better than that, it's a square matrix, it's 3 by 3. And what I want to try and do ultimately is try to figure out what is my matrix for C and what is my matrix for R. And in the process that we talked about in the previous video, we started by going column by column, reading left to right, and C is going to be those linearly independent columns that I can find. And so if I started with that same mindset, this first column again is always the first column in C. And if I look at the second column, we can kind of quickly see that the second column is not a scalar multiple of the first. So it is a new vector that can be included, that these have to be linearly independent. The problem is it's not completely evident that the third one is or is not a combination of the first 2. And this is where it gets really tricky, because in the last couple problems, again, it was really clear of like, oh, okay, well, this one plus this one. And I think I even did that in the example that I gave you at the end of the video, thinking that it was going to be trickier than it was. And it turns out it was like, oh, well, if you just add these 2 things, like boom, there's the combination. Well, here it's not as evident, because if I just straight up add these 2 original vectors together, 1 plus 3 is 4, but 2 and 4 make 2. 3 and 7 make 10. So like it looks like this last column is independent, but we need a better way to check for this. And so this is that procedure that I've been itching to try and do, because we need to know, is C of rank 2 or is C of rank 3? Because that means everything in terms of how we break these problems down. Now, the way that we're going to break these problems down is kind of along this mindset that if I take just these 2 linearly independent columns that we know are linearly independent, we're kind of asking ourselves, if I multiply it by some vector x, is it possible to get 4, 2, 6 as a result? Is 4, 2, 6 in this space? Is it in the span? One of the words that we used earlier. And the textbook simplifies this problem a little bit more by kind of breaking the problem down, and I'll kind of write it like this, as x times the first column, 1, 2, 3, plus y times the second column, 3, 4, 7. Is it possible for this to be equal to 4, 2, 6? Because we're really, in actuality, trying to solve this system. And part of linear algebra is always centered around solving a system. And so if I want to solve this system, one of the ways that I can do it is through the methods that we already know with systems, which is substitution and elimination. Substitution and elimination. Now, other than that, we have graphing. But in linear algebra, one of the huge concepts, and really one of the biggest ideas, is how elimination plays a role with matrices, how it's programmed, and everything is based around this key idea of elimination. In the process of elimination, we have three different, what's referred to as elementary operations. And primarily, we talk about these in terms of row operations. So I'm looking at what I'm allowed to do to equations, what I'm allowed to do to matrices, so that as I'm doing this manipulation, when I'm trying to eliminate, I'm trying to get rid of things, I want to make sure that I'm not changing the value of the problem. Like, I want to make sure that the matrix is still staying in and of itself that matrix, but we're changing what it looks like. For example, let's say I had an equation, so just to kind of put something brand new right here that we can extend. If I have x plus y is equal to 5, if I multiply the left-hand side by 2 and the right side by 2, so aka everything gets doubled, the solution to 2x plus 2y is equal to 10 is the exact same solution to the equation x plus y is equal to 5. In other words, changing the equation by multiplying everything by a scalar doesn't change the true value of the problem. The solution stays the same. This is one of the first elementary row operations. When I have a matrix, I can multiply any row by a constant and it does not change the problem. It's our manipulation technique, things that we're allowed to do. Well, another thing that we're allowed to do, and you learn this in algebra, is that if I have two equations or two rows, I can add these two things together, and the sum of these two equations that I get, in this case 3x plus 3y is equal to 15, would again have the same solution as the original system. So we're creating a new equation through this combination, but it doesn't change its true value. This is essentially the second elementary row operation. The third is essentially combining those two. I could take this top equation and I can multiply it all by 4 and then add, and we create a new equation, but that new equation would have the exact same solutions. We don't change the solutions to the system. And so when I'm working with my matrix and I want to perform elimination to help us discover what R is, and to better yet figure out what X and Y could be, we have to use these elementary row operations so we don't change those values of X and Y and we change our problem. And so how I'm going to write this, just to kind of simplify our problem down, is looking at this matrix as a whole. And there's a lot more terminology that's going to be involved, and we're going to build into this as we get into chapter 2 and chapter 3 and some of the consequences and results. So we're going to build on this, and this is what I alluded to earlier. When I'm looking at this matrix as a whole, I am going to eliminate this entry and this entry. Now, when I get to the answer from this elimination, hopefully I convince you as to why we took this approach. Part of it is because my very first number here is a 1, and it's going to allow me to zero out everything underneath that 1 using those elementary row operations. Now, to get this to be a 0, to eliminate that x, because remember this was that x column that I had written earlier, I can multiply the first row by -2 and then add to it the second row. So just to do that intermediate step, if I multiply this top row by -2, I would get -2, -6, and -8. And I would add to this the second row. So if I add, just going straight down, I would get 0, -2, and then -6. These three numbers, these three components, this is my new row 2. In other words, what I'm doing is I'm replacing this row by adding it with -2 times row 1. When we get into this unit, we're doing this a lot more. What you'll kind of see me notate is I'm replacing row 2 with row 2 minus 2 times row 1. That's the equivalent kind of idea. But in terms of an intermediate step here, I have 1, 3, and 4. I'm not changing that top row. Currently, I'm not even changing the third row, so that would stay the same. I'm only changing that second row. When I eliminate that entry here to make it a 0, I'm left then with -2 and -6 that we found through the addition. If I want to eliminate this 3 and make it a 0 as well, I'm going to approach the same mindset. If I multiply the top row by -3, I get -3, -9, -12. Row 3 was 3, 7, and 6. So because of my multiplication, if I replace row 3 by adding, I get 0, -2, -6, and this is my new row 3. So what I end up getting, because of space, I'm just going to drop this down. I get 1, 3, 4. My first row is not changing. My second row is 0, -2, -6. My new row 3 is 0, -2, -6. We kind of see the same numbers there, which we will find out is telling us something very important. But what we have kind of found out is, remember, our initial task was trying to figure out, is there a combination of these two first columns that give me the third? That question still applies even to this matrix here. Because we have changed what the system looks like, we're still asking the same question. These two columns are still independent. Is this independent or dependent as well? Well, if I reintroduce the x and y in our column notation, the column picture essentially, right now then I would have x times 1, 0, 0, plus y times 3, -2, -2. How is this going to be equal to 4, -6, -6? And I apologize about the space, but this is okay. Well, because we zeroed out, this is why we zeroed out these entries, notice that the last the bottom two equations here, formed by these vectors, would have 0x plus -2y is equal to -6. We can solve this now, which is what happens when we solve linear systems using elimination. We eliminate our variables, so my equations will result in a single linear variable equation. By dividing by -2, we get that y is equal to 3. Notice the third line would give me the same result. Well, if y is equal to 3, then I can use backward substitution in this first line here to find what x is. This tells me that x plus 3y should be equal to 4. And if I plug 3 in, we'll get x is equal to -5. Remember, x and y is representing, is there a possible combination to give me the third column? We found it. It's solvable. When I was reducing my matrix and doing elimination, the fact that these two rows came out to be the same thing also identifies that. And I'll mention that in a minute as we're kind of changing it. But right now, again, what that x and y is telling me is it's giving me the combination for the column of R. Because if I go back and I think about how we are breaking this matrix A into C times R, recall, again, that I had C. C is the first two columns, 1, 2, 3, and 3, 4, 7. It turns out that the third column is linearly dependent. So C only has a rank of 2. R, dealing with the rows, has a row rank of 2, where to maintain the first two columns being independent, I have my identity matrix, 1, 0, 0, 1. The x and y we found here is the combination we need to construct the third column in A. And if I do my multiplication, 1, 3, -5, 3, we get -5, notice how it's the dot product, row and column, plus 9 gives me 4. If I do this for 2, 4, dotted with -5, 3, I would get 2, etc. So this gives me and finds me R. Elimination tells me how to find R. Now, if I had a class, this would be essentially where I'd ask for questions, which was my pause, the long pause there. So if you have questions, shoot me an email. when I'm doing this elimination, I guess first off, just kind of notice, like in terms of finding C and R, which is what we were doing in the previous video, this is it, right? We've got it, right? We found the combination, we found C and R, but there's some really interesting things that we can continue to build on, especially when it gets down into that elimination matrix that we had. So I'm going to put that elimination matrix back up, but just understand that in terms of the original question, how do I find R? We found it, like we have it. So everything from this point on is more of an extension, starting to ask the bigger questions that linear algebra is looking at. And that realization of when a matrix looks this way, what it's actually telling us when we're digging into those numbers. Now A, remember, we were able to reduce. Now the book calls the reduction B. And so when we reduce into that matrix 1, 3, 4, 0, negative 2, negative 6, 0, negative 2, negative 6. Again, the book refers to this as matrix B. Now, it is possible to continue the elimination process. If you think about how we eliminate specifically a system of 3 equations and 3 unknowns, or this is x, this is y, and this is z, once we eliminate one variable for x, the idea is that we can eliminate then the next variable, which if we're reading left to right would be y. So when I'm looking at this problem, I have this first row good to go. If I focus on the second row, I want to eliminate the y underneath this negative 2. Again, we'll talk more about this process, but if you notice, we're essentially looking at this main diagonal. We want to zero out all of the entries underneath. We end up creating an upper triangular matrix, and that's something that's going to be very important in chapter 2 and chapter 3 and on when we're dealing with this. So I want to eliminate this negative 2 right here. I want to get rid of this y and create this to be a 0. Well, I can do that pretty easily by multiplying this row 2 by negative 1 and adding it with row 3. And so if I do that elimination process, I get 1, 3, 4, 0, negative 2, negative 6, and then I would get 0, 0, 0. Because these entries are the same, if I subtract row 3 minus row 2, then row 3 becomes all zeros, right? It's all gone. This matrix is technically upper triangular. I have only zeros below the main diagonal. But better yet, there's a little similarity. If I cover up this row of 3, how it becomes a 2 by 3 matrix, which is really similar to R. So the question kind of arises, can I transform this matrix into R? Well, I can. Notice, if I take this second row, one of the elementary row operations was all about multiplying by a scalar. So it is possible to change this entry and make it into a 1. I can do that by dividing everything in this row by negative 2. If I divide everything in that second row by negative 2, first row stays the same. Second row becomes 0, 1, 3. Third row is staying the same. Well, I'm very, very close to this little quadrant right here being the identity matrix, just to make my ones the same. The issue is that this needs to be a 0. Well, not only can we eliminate going down, we can eliminate also by going up, which is why it's a lot easier to make this diagonal entry a 1 before we begin to do that elimination. I could have done it here, but that process would kind of suck. So instead, we're going to look at it here because numbers are going to be a little bit easier. If I want to zero that entry out, I'm going to multiply the second row by negative 3 and add that with row 1. Now what's really, really important with that is notice by multiplying this row by negative 3, this entry does not change. This number will stay a 1 because I'm going to do 1 minus 3 times 0, which is still 1. It's huge. The entry that will ultimately get zeroed out that we want is this one. So again, I'm going to do row 1 minus 3 times row 2. So when I do that change, (1, 0, 0, 0, 0, 1, and 3), 3 minus 3 times 1 is 0. 4 minus 3 times 3 is negative 5. And this should immediately stand out. Essentially, the idea is what I have now is my upper triangular matrix for A through elimination. Now, if I take off this 0 row, because if everything is 0, then this equation does not add anything to my overall system, and it doesn't add anything to my overall matrix, then what I have is R. If I include the zeros, then we refer to this as R0. It is my row matrix, but it contains the 0 rows from the elimination, thus the index there of 0. I will always make the mistake of reading that as R0, just because that's my academic training in physics and applied sciences and calculus, etc. But I will try to be specific and call this R0 instead to really kind of emphasize that 0 row when we're doing it. But the second that I take that 0 row out, R0 becomes R. So how do we find R? By taking our matrix for A and walking through elimination to get the identity matrix. And in getting the identity matrix and zeroing out what we can zero out, what we are left with is R. Now, by doing the process like we did, this form that we get is essentially this process of putting your matrix in what is essentially called reduced row echelon form. My brain had to think about the order. Reduced row echelon form. The process that we got our matrix into when we were here, so 1, 0, 0, 3, 1, 0, 4, 3, 0. So notice how the identity matrix is not here yet. This is just reduced echelon form, or row echelon form. I need to double check. Row reduced. I feel like I butchered this language. So we have reduced row echelon form, or RREF. It's just row echelon form when we're like this. Typically we try to take it to reduced. But again, something that we're going to talk about a lot a little bit later. So taking your matrix into reduced row echelon form through elimination will tell us what R is and tell us what my linearly independent columns from A are. We can find C. Now, one of the things that the book then kind of gets into is two really important facts, as well as underneath that talking about a couple key things with R and R0 and some facts from that as well. The thing that I want to really kind of hit on is this term for basis and this term for dimension. We haven't really defined dimension that much. We will later. Basis, we will do so as well. The R columns of the R columns of C form a basis for the column space. They form a basis, and it has dimension R because there are two vectors. But if I take this and multiply it with any vector, it can give me any vector in the column space, any multiple and linear combination that we want. This being the row space, we can also find that. So span and basis kind of go together, and we'll see that a lot later. One thing I mentioned a little bit earlier as well is when we're solving a system of equations, notice how that kind of plays a big role underneath the hood here. This is going to come back when we're solving that AX is equal to B form. The last thing to mention in this lesson that he mentions in the textbook is this is all about matrix multiplication and how we multiply matrices together. And he outlines in the textbook that there are four main ways, and we've kind of seen those four main ways, or at least three main ways, up to this point. And it's the fourth way that I will quote him as saying it's the way that most people tend to not know. But what it ends up giving is what's referred to as the outer product when multiplying with matrices. One of the common terms that we'll need a little bit later on called the inner product. Inner product also, I think, is seen in multivariable, Cal 3, deals with doing the dot product, which is more of the standard that I had mentioned in the previous videos. of that when I'm doing a matrix times a matrix, you mostly go row by column and we do dot products. And through those calculations, if I'm multiplying a matrix that is M by N with a matrix B, N by P, the count of how many times we do some small multiplications is M times N times P. We saw this with a 2 by 2, and in doing that multiplication, we had a 2 times 2 times 2, or 8 total multiplications being done. Well, if I'm doing this for any matrix, the inner products, this will follow. The outer products actually does the same. So again, the number of multiplications does not change, but how we view the multiplication and perform it does. Now the result, again, is the same, which is really, really fascinating. And so just to show what this looks like, instead of multiplying row and column, we actually go column and row. Column times row. And when I'm doing this, as we multiply the column and rows together, we're adding those results together. And so I think he gives one example. I'm going to use the previous example that we just had, where we had my matrix A again was 1, 3, what was it, 4? Let's see, 1, 3, 4. Yep. We've got 2, 4, 2, and 3, 7, 6. And we essentially factored this or broke it down into the first two, 1, 2, 3, 3, 4, 7. And then this is not a lot of space. Let me make some more space for this. Here, I'm going to erase this. So again, we had A was 1, 3, 4. This was 2 and 3, 4, 7, 2, 6. We had this broken down into 1, 2, 3, 3, 4, 7. And then my matrix R, which is 1, 0, 0, 1, and then 5, negative 3. If I remember that order correctly, or was it negative 5? Negative 5, 3, apologies. There we go. Traditionally, again, and I showed this actually when we were checking to see that it worked, you typically think row, column, row, column, row, column. But what he is actually showing is that being the inner product, if I want to do the outer product, I'm actually going to go column by row. So what that would look like is 1, 2, 3 times 1, 0, negative 5. And what I would do with this result is add this to the second column, 3, 4, 7, times 0, 1, 3. So if I go through and I do this multiplication, 1 times 1, 1 times 0, 1 times negative 5, 2 times 1, 2 times 0, 2 times negative 5, 3 times 1, 3 times 0, 3 times negative 5. What it's starting to compute is the combinations to construct this vector. Notice how this column is all zeros because that first row is essentially equating how we get this first column, not the second one. Remember, this column and this column are completely independent for R, which is why we don't see that anything happening there. Well, if I then add 3, 0, 3, 1, 3, 3, 4, 0, 4, 1, 4, 3, 7, 0, 7, 1, 1, 7, 3. If I add these two things together now, apologies, it's terrible looking 7. Oh, my math is terrible. Let's see if this, double check me. So 3, 4, 7, 0, 1, 3. So 4, 12. So that works. That works. Oh, I screwed up here. So 3 and negative 5 is negative 15. So, so I know we were supposed to get 6 there. I had negative 5 and 21, which was not coming out. So I'm going to absolutely leave all this in the video because I am 100% human and totally had a brain fart on that. If I add these two matrices together now, notice this column will go unchanged. This column will go unchanged. The third column is being created as a linear combination of the negative 5 and 3. This results in A. So we get back to the same exact matrix using the exact same number of operations in terms of multiplications that we would if I was to do row by column, row by column, row by column. And you may be asking, and I really hope that you're asking this or thinking about this question, this way seems way more complicated. We did that row column pretty quickly earlier with no mistakes, and I sat here for probably a really awkward 30 seconds to a minute of staring at this one trying to find the mistake because this number felt so weird. So like, why have this other approach? And some of it stems around this idea of outer product and what it can tell us when we're working with vectors and we're working with matrices. The other way is to actually see that if A is a rank 2 matrix, recall that its column space only has 2 vectors in it. This is a rank 1 matrix. This is a rank 1 matrix. So what this outer product is showing is that idea from earlier that any matrix of rank R is the sum of R rank 1 matrices. We see it in the outer products when we're actually computing this. And so I think it's a really beautiful thing to kind of see in how we do these multiplications and how it actually works. The textbook then kind of gets into a note about the matrix R, which I've essentially mentioned, and shows this for another multiplication, specifically in example 5, done in yesterday's video. He ends it with 4 ways to multiply a matrix AB to result in C, and so I just ask that you review that. I think it's a good setup and a good visual for how we can do that multiplication, row by columns or columns by or rows by column in terms of the matrix. So take a look at that, and then take a look at the practice problems, and that'll finish this off for Unit 1. So as far as MD Online goes, your first summative is online and available, so work through those problems and then turn them in when you're done.